Hello and welcome to today's session. We are looking at blackbody radiation. There are four objectives for today's session. Define the term blackbody, describe how the shape of a blackbody curve changes as temperature is increased, use Wien's displacement law to estimate blackbody temperature of sources, and to use Stefan's law to estimate the power output of a star. So first of all, we'll start off with the definition of a blackbody. As I said, with every chapter, every part of physics we've done so far, there's 1 to 2 mark definition questions. So defining a black body, then we can say that it's a body that absorbs all wavelengths of EM radiation and can emit all wavelengths of EM radiation. So we can assume that a star behaves as a black body. Pure black bodies are going to radiate radiation in a strong and well-defined way, and we'll see that you can plot a curve for this. So a curve and then estimate the power output from that curve. And as I said, we're treating stars as black bodies. So we can look at the emission of radiation from stars and we can do some spectral analysis. So if you think back to year 1 when we looked at energy levels and spectra for certain transitions with electrons and energy levels, you can see the absorption and emission spectra and work out what particular elements are in the star. So that can be a question that comes up in astrophysics. You might have to describe how you get absorption spectra and describe what the process that's involved. So a bit of year 1 thrown into astrophysics. So you can plot a curve of black body radiation. Essentially what you plot is the intensity versus the wavelength, and it's known as a black body curve. And it's dependent on the temperature. So in some of the lessons that previously we talked about, bluer stars are much hotter in comparison to a yellower star like our sun. And if you look at the blackbody radiation curves, you'll see a shift more towards the left for a hotter star and more to the right for a cooler star. So we can use these curves to do a quick judgment on which star is hottest. So typical exam questions, you'll have a blackbody radiation curve. There may be 3 or 4 stars on the curve, and you have to state for 1 mark which star is the hottest, and then additional marks will be in there for calculating the wavelength of that star, so the peak wavelength for emission of radiation from the star. So this is the blackbody curve shape. As I said, a shift more towards the left for a hotter star, and you can see the intensity on the y-axis and wavelength on the x-axis. So lower wavelength, greater intensity of the star. You'll see the dotted line, which is Wien's displacement law. That is related to the wavelength for the peak energy output of the star. So that's what we'll look at. So for these black bodies, as we said, for a hotter star, it's more shifted towards the lower wavelength. So think about what we've looked at with energies of photons. Higher energy photons are high frequency and lower wavelength. So that's going to shift more towards the left. The peak is higher as well for a hotter star, and the area under the graph gives us the total energy radiated per unit time per unit surface area. This brings us on to Wien's displacement law. This equation is on your formula sheet, and as I said just a few minutes ago, the peak wavelength is the wavelength at which the maximum energy is radiated. So this law can give us the peak wavelength of the star, inversely proportional to the temperature in Kelvin, and you'll see that at the end it says mk, so that value is in meter Kelvin. So meter Kelvin, and it's 2.9 times 10 to the minus 3 meter Kelvin. So what you'll need to do, you might be given temperature of a star, find the wavelength, and that's what we'll do next. So just a quick example using that equation. What is the peak wavelength of a black body emitting radiation at 2000 Kelvin, and in which or what part of the EM spectrum does this lie? So again, we're going to use the equation which is on your formula sheet, so you don't need to memorize it. So lambda max multiplied by T is equal to 2.9 times 10 to the minus 3 meter Kelvin. Then we're trying to find lambda, so we're given the temperature, so it's 2.9 times 10 to the minus 3 divided by 2000. So they could give you a temperature in degrees Celsius, but you'd have to convert to Kelvin, so just be aware of that. Put that into your calculator and you get 1.45 times 10 to the minus 6 meters. And then that puts that in the order of the infrared region. So that's in the infrared region. And for the exam question that you'll have, the submission this week, you'll have to use this displacement law and also Stefan's law, which we'll come on to in a moment. With the luminosity of stars, luminosity is basically a measure of the energy output. And as that energy output increases, we can think about the power, that power increases. Luminosity increases with temperature, and this gives us another law, which is on your formula sheet, called Stefan's law. Stefan's law, basically, that total energy per unit time radiated by a black body is proportional to the fourth power of its absolute temperature. So you'll see Stefan's law on your formula sheet, and it's got temperature to the power of 4, and we'll have a go at using it. So Stefan's law, basically, if you double the temperature, the power goes up 16 times. So luminosity is equal to sigma times the area times temperature to the fourth power. This is on your formula sheet. And Stefan's constant is on your formula sheet as well. So applying this to stars, we treat stars as a perfect sphere. So it's just going to be 4 pi r squared sigma t to the fourth power. And that's what we'll do. So again, we're making some assumptions. So it's perfectly spherical, and we can calculate the energy output by treating it as a black body. So that's our first assumption. It's a black body, and then it's a perfect sphere, and we can apply the equation to it. Okay, so we've got a question where we're going to have to put all of the relationships into use. The first part, we need to find the power output from the sun, so we're going to use Stefan's law. Then once we've got that power output, we can find the power output per unit area, dividing that by 4 pi r squared. And then the peak wavelength, we'll use Wien's displacement law to find the peak wavelength for the sun. So going through this then, we want to find the power output for the sun, and we're given the radius, we're given the temperature, so we're using Stefan's law, and L is equal to the area times Stefan's constant, which is given to you on your formula sheet, T to the 4. So remember, we said that we're treating the star as a perfect sphere, so it's 4 pi r squared for the area. Times that temperature to the 4th power. This will give us the luminosity, which is the energy output. That energy output is going to be in watts, so that's the unit. Put that into your calculator, and I've missed out the constant. So Stefan's constant, I've missed that out in there. So Stefan's constant, which is 5.67 times 10 to the minus 8. So yeah, Stefan's constant. Then put that into your calculator. So area, we've got Stefan's constant in there, we've got the temperature to the 4th power. Put that into your calculator, you'll get a value of 4.47 times 10 to the 26 watts. So that's our power output. Okay, then power output per unit area, that's basically an intensity, because you've got the power output and we're dividing it by an area. So power output per unit area, we've got the luminosity from the first part, so we know that's 4.47 times 10 to the 26. All we need to do is divide it by the area of the sun, so the surface area of the sun. So 4 pi times 6.96 times 10 to the 8. That needs to be squared. Gives us a value of 7.34 times 10 to the 7 watts per meter squared. Final part, what is a peak wavelength? So when you're using Wien's displacement law, so lambda t was equal to 2.9 times 10 to the minus 3 meter Kelvin. So again, this is the maximum wavelength of the star, so the peak wavelength that's going to give out most of the energy. So lambda max 2.9 times 10 to the minus 3 divided by the temperature of the sun, which is 6,000 Kelvin. That was given to you in the question, and we get 4.82 times 10 to the minus 7 meters. Your task for today then is to complete the Blackbody exam style question and upload it via Turnitin. If you're having any difficulties, drop me a message via Teams or email and I'll get back to you. Take care, and I'll see you on the next one.